Moving on to question number 5 of RACE-1 from the Secureum Bootcamp. So we again have several issues here from which we should select which one are actually present in the code base. We have option A, which says that a front running allows one to pay less than expected for tokens. Now this sounds like there should be some MEV kind of thing going on here where someone can, or it sounds like you are actually the front runner, that you are able to front run someone or maybe sandwich someone, and that somehow allows you to pay less than expected for tokens, which is a little bit weird because usually these kinds of trades are done as like an arbitrage and stuff like that. So buying the tokens cheaper than expected with front running sounds kind of weird, but either way, usually when you do these kind of sandwich or front running attacks, what you need to do is you need to be able to manipulate the price, because how those attacks usually work is that someone is sending a transaction to the memory pool saying that I want to buy X amount of tokens for this amount of other tokens, and then they have specify some sort of spread that they are willing to pay if the price changes before the transaction actually hits the chain. And front runners make use of the spread. They exploit the spread. They see, this person is willing to pay this much more in case that it rises, and then they basically make the price rise to this maximum, to the maximum spread that they can get out of it. And well, then there's the person who was trying to buy tokens is paying extra basically because they set the spread too large. In this case, we know that this kind of front running or sandwiching attacks aren't possible because we know that the price here is static. It's always 1 ether equal to 10 tokens. So no amount of front running or sandwiching will be able to manipulate the price to anything else. Maybe they will be able to do it on a DEX that is dealing with this token, but not with the token directly. So option A does not sound like a valid option here. Then we have B, which says a lack of access control allows one to receive tokens for free. Now we already have found a bug here in the previous question where we can receive tokens for free, but access control wouldn't have prevented this, especially because all of the functions that we have in this contract, we have the transfer function, we have the buy function, all of these functions are intended for public usage. None of these functions are supposed to have an access control that restricts them to an administrator or stuff like that. The only scenario where this option would be valid is maybe if the token has a minting function where users can just mint arbitrary amounts of that token, and this function should have been restricted to be only callable by an admin, then indeed there would be a lack of access control. But in this specific case, access control lacking doesn't really make sense, so option B is as well incorrect. Then we have option C, which says incorrect balance update allows one to receive new tokens for free. So somehow the balance is updated correctly, and this balance update allows to receive free tokens. So there are two places in this contract where the balance is updated. Once in the buy function, when you buy new tokens, obviously. We can see here that the balance is updated in this line. We update the current message sender's balances, and we do this by taking the current balance of the message sender and safely adding the desired token amount, which comes from here, from the buy function parameters. So we already found a bug up here with the rounding down that happens in this line, with this division, but this doesn't have anything to do directly with the balance update itself. And the balance update itself here doesn't have a problem either. It's using safe add, which is a correct implementation of this, how would you say, integer overflow protection basically. So that's fine too, and this entire line looks okay. Now the other place where balances are updated is here in a transfer function. And something interesting happens here because it says here that they are saving the balance in a local variable or in local variables so that they can reuse them multiple times without paying for S load on every access. So basically they're saying that every time you're accessing the balance of someone, like the message sender's balance here, because balances is a storage mapping, so every time you would do that, you might have to load it from storage using an S load operation, and that is expensive. And so the intention here seems to be to save gas by loading them only once and then using them here multiple times. And that doesn't sound a bad idea at the first glance. And if you play this scenario through where a person is sending to another person an amount, this completely works fine. But where this falls apart is when a person is sending themselves token. We can quickly go through this. Let's say we own, so we are message sender and we own 10 of these tokens. And let's say that we call this transfer function with an amount of 10. So we are transferring all of our tokens to ourselves. So we are transferring them to the message sender. So balances 2 is as well 10. The require here says that balance from needs to be greater or equal to amount, which is true, so that passes. And then we will arrive here, which says that we are subtracting the amount from balance from, so it's 10 minus 10, which is 0. So we are updating our balance with 0, and I guess that sounds fine as well, as long as we add the 10 again later. But what actually happens is that we then save add balance 2 with amount, which means that we're doing 10 plus 10, which is 20. So instead of updating this 10 back into 2, how it is supposed to be, because we are sending ourselves the same 10 again, we are instead summing the previous amount that we had and the amount that we're sending, and we're doubling the amount of tokens that we have. And this is all due to the optimization that was done here. And this is actually a real world thing that still keeps happening from time to time, where people think, they're really smart. They're doing some optimizations here. And what they actually end up doing is introduce issues with the optimization. So very dangerous, as you can see. And that's also why it's very important to think about the edge cases, because in the usual case, in the expected case, when you send your amount to another person, this works fine. But security reviews are all about the edge cases. What happens if I do something unexpected? What happens if I actually send something to myself? Those kinds of edge cases are really important to test. So therefore, there's indeed an incorrect balance update that allows one to receive new tokens for free. Therefore, C is correct and D cannot be correct, and that is question 5.